Saxon Algebra 1/2, Lesson 89. Hi Caleb, we're back from spring break. We're going to push through for another, 6 weeks or so with math. So fire up, get excited. Before we jump into Lesson 89, which is super straightforward, I would like to take a minute and just review a couple of the problems on the midterm where you jumped off the wrong cliff. And there were just a couple small things on the second time. We didn't even talk about the first test. I don't know what happened then. But I'm glad that you wanted to take it, and I'm really happy with the results you had. But I know that you're a guy who likes to get things pretty much perfect, I think, if I'm reading you correctly. So I want to just walk through the problems where you took a wrong turn and make sure you understand exactly what happened. So the first problem was the biggest issue. Let me just remind you of what was happening. The figure shown on the left is the base of a right solid 10 meters tall. Okay, so this is our three-dimensional thing. It's 10 meters tall. This is the base of it. What is the lateral surface area of the right solid? Okay, lateral means side. So what we're saying is, forget about the area of the top and the bottom. We just want to know this. Imagine it's made of cardboard. We get out our box cutters. We cut out this like teardrop shape at the top and the bottom. And we just open up that cardboard. Magical lay flat cardboard. So there's no, it doesn't like curl up and act all weird. It's nice and straight and flat. So this is the cardboard. It wraps around this shape. And here it is. Once we've cut it open, we cut it right here, let's say. It doesn't really matter where we cut it. But let's just say we cut it right there. And then this is the part that used to wrap all the way around. And then this is the seam that used to be attached right there. Okay, this is the lateral surface area of the right solid. We need to find the area of this. Okay, the area of a rectangle is length times width. So I write down my formula inside the box because that helps me remember it's the area. That just helps me. Okay, so what we need to do is we need to find the length, which is going to be down along here, and we need the width. It really doesn't matter which you call the length and which you call the width, as long as you recognize you need both sides of the rectangle. This is the easy part. It's 10 meters tall, so that's the dimension right there. This is the harder part because we have to do a little bit of calculation, and we know it's going to wrap around like this, right? So we have to find the perimeter of this object like so. Pretend it's exactly on there. In order, that will be equal to this, right? The perimeter of this shape will be equal to the distance of that dimension. So we need to add not the area of the triangle. We don't need all of this. We just need the length of this side and the length of this side. So 10 plus 8 plus the circumference of the semicircle, which you correctly calculated as 9.42. Okay? What you got confused about was that you wanted to take the whole area of the triangle, and that's what you calculated. We don't need the area of the triangle. We just need those two sides. Okay? That was where you got waylaid on this problem. No need to take the area. We just need those sides. So 10 plus 8 plus 9.42 equals, let's see, this much is 18 plus 9 is 27.42. Yes. That is the total length. And 10 is the total width. So then we do 27.42 times 10 equals, let me just slide the decimal place, meters squared. That's what the correct answer was. All right? So your problem was all in the triangle, the semicircle you did perfectly. You multiplied it by 10 perfectly. You just calculated the area of this instead of just adding those two sides. Okay? Problem 1. Problem 4. Most of these other problems where you lost points was simply a matter of not showing enough work before I want to show you just what I would have liked to have seen. This was Lee sneezed 23 times in 8 hours. If he keeps this up, how many times? Use the proportion method. What I was looking for is you to go, okay, 23 times in 8 hours equals X times in 24 hours. That's what I was looking for. What you gave me were two rates. 23 times in 8 hours equals 8 times in 23 hours. That's true. That's correct, but that's not using the proportion method, right? And then I saw your work here, 3, and you multiplied it by 3. The right calculation, and that got you the right answer, 69 times in 24 hours, but you didn't show me how you brought those numbers together. So this is what I would have wanted to see. 23 times in 8 hours equals how many times in X hours? Then I would have wanted to see you cross multiply. 23 times 24 equals 8X. And then I would have liked to see you divide, and that would have been 3. 8 times 3 is 24. That would have become a 1. This would have canceled, and then we would have had X equals 23 times 3, 69 times. Okay? That's what I was looking for. I only took away 1 point because I could see where you were going. This calculation was correct. I just took away a point. I did not see this anywhere, and you didn't show me enough of your thinking. All right? So that's what happened there. Then the other problems, you did really, really well. Here, it was when we got to 8 and 10. And the reason I gave you as many points as I did on these problems is because, Caleb, I really liked your diagrams. You did a great job in showing me. See, I saw this erasing back here. That made me curious. Whenever there's erasing going on, I can see you're waffling in your thoughts, and I don't want a waffling student. Point of reference, Caleb, teachers and college professors are human beings, and we can't help but be influenced by what clues we see going on in our students' work. So when I see erasing like that, it makes me curious. I would much rather that a student leave it written out and I could see what they were thinking, because usually what happens is I'll notice what they were doing wrong, and then I'll see, oh, they corrected it. But when I see erasers, it makes me curious, and to be honest, it makes me lose confidence in what a student's doing. So I really advise against erasing. Okay, but going on, you did a great job with your diagram. The number increased from 400 to 280. What percent increase was this? And you did a really nice job of breaking it out to show if 40 was the original 100, then in the new diagram, 40 is still the original 100, but there's another 240, and that represents 600. That is good. That is what I was hoping to see. What I also wanted to see, though, was this. I wanted you to go, oh, this is a case where we need the frickin' formula. And I wanted to see the formula. Okay, and then I would have liked, the way I would have done it is I would have said, okay, let's say that we're trying to find the percent times the original number equals the new number, right? And then I would have solved this, 100 over 40 to get the reciprocal of those, 100 over 40. This cancels, this would have just been p by itself. 40 into 287, so I would have found that the percentage, the new number was 700% of the old number, but the increase, since the old number represented 100%, the increase was 600%. Okay, that's what I would have wanted to see, and I would have wanted to see the diagram. You saved yourself by showing the diagram really well, even though I didn't get a calculation. That's why I took off half a point. And then the same thing goes for problem 10, which was a similar kind of problem. Coach asking his team to give 110% of their previous effort. You did a great job with the diagram, and you did this breaking apart to show the original effort and then the change, the increase as a separate part. I really like the way you did this in the diagrams. Again, that's why I gave you as many points as I did. I would have liked to seen the formula, and then I would have liked to see you work it through algebraically. These are the right answers, but I don't understand how you got them. Okay? So, 3 of the 4 problems where you lost points was simply a matter of how you documented. The only problem where your brain went sideways was this first one where you took the area of this. You used base times height over 2. You just got confused about what you were trying to do. Okay, so great job. I'm really pleased with your comeback on the midterm. Very happy with that. No more things to say except carry on. Okay, let's do lesson 89, which is something that sounds really hard. Trichotomy axiom. And I will say what I've said to you before. Whenever we get words involved in math, it usually doesn't lead us to a happy place. Numbers and symbols will tell us everything we need to know in a really condensed language. Words make simple things hard. Here's what the trichotomy axiom is trying to tell us. If we have, let me just write it out. Super precise. I'm going to add that. If we have 2 real numbers, and we're going to call them A and B for now, because this is applying to all numbers, only one of these things is true. Either A is less than B, A is equal to B, or A is greater than B. Please give me a Homer Simpson moment of, duh, of course this is true. This is so obvious. Why we give it this big fancy name is beyond me. But only one of these things can be true. It's either less than or equal to or greater than. It can't be, that's just simple, right? So, we have a new kind of symbol that we can use, and it's called the symbol of negation. And let's use an example. If A, the way we read this is A is not greater than B. All right, so how do we write this as a positive symbol instead of this symbol of negation? Because once we see these symbols of negation with the slash through them, we want to get rid of those. We want to restate the problem in a positive tone instead of a negative tone. So we just mentally go to this list in our head and go, okay, well, if it's not greater than B, then we have 2 options. A could be equal to B, or A could be less than B, right? That's just using this. Obviously, it's not hard. And we have a new symbol. I think it's new to you. I don't think I've used it with you. Maybe you've seen it before. But we have a new symbol that says, okay, if you're trying to smush less than and equal to together, you can write it as this, right? We just kind of put them together. A is less than or equal to B. It means that both of those are true, all right? So instead of A is not greater than B, we write A is less than or equal to B. So that's how we deal with symbols of negation. Let's try another one. Let's put numbers in. 4 is not less than or equal to 1. Okay, we know that's true by the values, but we also know from the trichotomy axiom that if it's not less than and it's not equal to, then we must be able to say 4 is greater than 1. Okay? Pretty straightforward. So in these problems, we're just going to be graphing some simple expressions, but we're going to have some symbols of negation that we'll have to fix before we draw any pictures. So here's 89.1. Graph on a number line. X is not less than 2. Okay, I mean, if you want to look at this written down, you can, but honestly, it's just in your brain. You know this is true. If it's not less than 2, then X could be greater than 2, or it could be equal to 2. Okay? So we put the other 2. If we're negating one option, then we have 2 others. If we're negating 2 options, then we only have 1 other, because there's 3 in total. Okay, so if X is not less than 2, then X could be greater than or equal to 2, and we can graph that on a number line like this. We'll put 2 here, we'll circle it, we'll fill in the dot, and then we'll go greater than. Make sense? 89.2. Graph on a number line. X is not greater than or equal to minus 1. Okay, then that means X is less than minus 1. And so we draw the picture. Here's our minus 1. You don't have to put a lot of detail. Oh, I wrote minus 3. All right, fine. We'll just fill it in. X is less than minus 1. Okay, there's no equal sign there, so we circle it, and we go that way. Okay? Sometimes students ask me with these signs, like this one, would it ever be possible that they negate only part of it and say that part's true? No, it would never be tricky like that. If there's a negation sign at all, then it negates the whole sign. And sometimes it's hard to see in the textbook because the symbols get kind of small and scrunchy. So there's no tricks like that. 89.3, this is our last example for the lesson. Graph on a number line. X is not less than minus 2. And this is the way we say that. X is not less than minus 2. And so that means, thinking of our trichotomy axiom, if we know it's not less than, then it could be greater than, but it could also be equal to. Minus 2, and then we graph. Minus 2, the equal sign means that we color in the dot, and we go like so. Yay, those are all the right answers. I didn't smiley face them up. But that is lesson 89. Let me go back and just make sure. Yep, we got them right. Okay, trichotomy axiom. Don't let the names scare you. It's fun.